right, I may be a few seconds early, but let's start with today's lecture. Today we're going to continue with pipe frictional resistance and how we describe that in the energy equation. Up until this point in time, we've talked about the Darcy-Weisbach equation, and we will continue to use that. However, I also mentioned in previous lectures that there's another method that is commonly used by the old timers in this country, and you just need to be aware of it because you may run across it when you're reviewing old designs or when you're looking at some of the options in some of the software packages. They allow you to select this method. So I would be remiss if I didn't go over it, and I want to underscore that the Hayes and Williams method is not in your textbook. So the only references you will have outside of this lecture would be to go to the internet, whereas there's a mountain of information on this method. So for the Hayes and Williams method, remember what we're trying to do is describe friction losses. And the Hayes and Williams equation, which is in the handout for today, is in a substitute for the Darcy-Weisbach friction equation, as you'll see. So all we're trying to do is use another equation to calculate these friction losses H sub F. So for the Hayes and Williams equation, and again, this is right off of your handout, the velocity is equal to a constant 1.318 times the roughness, the Hayes and Williams roughness coefficient, times the hydraulic radius, times the friction slope. So the equation as you see it has our system of units, feet and seconds. You have to know that. And in the handout for today, I also give you the SI form of the equation. And aside from the dimensions, the only difference is the multiplier in the beginning of the equation. So in this equation, you have velocity in feet per second. CHW is the Hayes and Williams roughness coefficient, and it is dimensionless, just as the Darcy-Weisbach friction factor is a dimensionless friction coefficient. RH, we have mentioned before, it's the hydraulic radius, and we'll be talking more about that today. But for any cross-section, hydraulic radius, or sometimes called the hydraulic depth, is calculated as the cross-sectional flow area divided by the portion of the cross-section wetted by the fluid, what's known as the wetted perimeter. And S of F is, or S, as you see in the equation above, is known as the slope of the energy grade line. It's also known as the friction slope. And it's dimensionless, but this is where the friction loss is buried. So you can certainly rearrange this equation, and you will see it rearranged later, to solve directly for H sub F, just as you saw in the Darcy-Weisbach equation on the previous slide. H sub F is directly solved for in the equation. Okay? So again, this is the Hayes and Williams equation, and this is the common form you find it in. So the Hayes and Williams roughness coefficient is also on the handout for today. So I'm going to exit the PowerPoint so that I can open up the PDF for today. And hopefully everybody can see that PDF. If you can't see the PDF, write it into the chat box so someone can let me know. But at the top of the handout, again, you see the Hayes and Williams equations as I just had shown you on the previous slides. Down below, you can see the equation in SI. And what I want to get to is on the rest of this handout, on this page and the next, you see Hayes and Williams roughness coefficients. The interesting thing, if you look on these rows where you have cast iron pipe of different ages, from new to 40 years old, what you see is as the pipe ages and the inside corrodes, which means the relative roughness is getting larger, the Hayes and Williams coefficient gets smaller. So large Hayes and Williams coefficient, small friction loss. Sorry, small friction loss. Large Hayes-Williams coefficient, small friction loss. In contrast, for Darcy-Weisbach, the smaller the Darcy-Weisbach friction factor F, the smaller the head loss. So just recognize there's this inverse relationship between the two. And if you equate H sub F if you equate the Darcy-Weisbach equation to the Hayes-Williams equation, let H sub F of one equal H sub F for the other, what you can do is tease out the equation that you see on the center of the top page, where the Hayes-Williams coefficient you can see is inversely proportional to the Darcy-Weisbach friction factor. And I'll be speaking more about this. And in fact, since I have the PDF open, let's identify it now. What the Hayes and Williams equation does is remove the necessity to understand the boundary layer. What I mean by that is, it doesn't matter if you have laminar, transition, or turbulent boundary layer, which means you don't need to know the Reynolds number. So in this case, the Hayes and Williams roughness coefficient, CHW, is only a function of basically the absolute roughness case of S. And the absolute roughness is described by the material in this table, the left-hand column. That's what's defining case of S. So again, this table crosses two pages, and on the bottom of the second page, what you can see conveniently plotted is the Hayes and Williams roughness coefficient plotted on the Moody diagram. And so you would think that, by the way it's set up, Hayes and Williams roughness coefficient being constant, that it would be out in the turbulent zone where all these lines and all the Hayes and Williams lines would be horizontal, but they're not. Basically, the best fit between the Hayes and Williams and Darcy-Weisbach seems to be somewhere in the transition zone for a very, very narrow range of Reynolds number. And so the moral of the story is, don't mix and match. You will always get a different answer for the same problem if you use Hayes and Williams and Darcy-Weisbach. You're always going to get a different answer. My opinion is that Darcy-Weisbach is doing a much better job of describing energy losses. However, again, Hayes and Williams is used more often than not, and I'll explain why that is as we go back to the PowerPoint. So hopefully you can see the PowerPoint now, and the slide I was on, I was talking about the Hayes and Williams roughness coefficient. So just as before with Darcy-Weisbach, we had a problem, and part of the problem is you know the material, so you know the absolute roughness from which you can get the relative roughness. For Hayes and Williams, all you really need to know is the material, which again is absolute roughness, and then you can move ahead. So with closed conduit problems, remember, before we indicated there's three classes of problems when we're talking about friction loss. Calculate the friction loss, calculate the discharge, calculate the pipe size. It's the same three problems with Hayes and Williams. So the classes of problems are exactly the same. It's just which construct, which equation you are using to describe friction losses. What's interesting is because all of these solutions now using Hayes and Williams is using an equation that only uses absolute roughness, all of these equations are direct solutions. You don't need to combine equations like we did with Darcy-Weisbach and, say, Swamy and Jain. You do not have a trial and error solution in any of these cases. So, again, as I pointed out on the handout, if you let H sub F Hayes and Williams equal H sub F Darcy-Weisbach, you come up with this equation. And this is why the Hayes and Williams contours on the Moody diagram of the handout plot as diagonal lines. This is basically Reynolds number. velocity times diameter over nu is basically the Reynolds number. And so what's happening is the plot of Hayes and Williams on this Moody diagram is a sloping line. It's not a horizontal line. And for water applications, I did not give you this equation in your handout, but what you can see is we can relate the Darcy-Weisbach F to the Hayes and Williams coefficient. Everything on the right-hand side is dimensionless, and again, Darcy-Weisbach F, Hayes and Williams roughness coefficient are both dimensionless. So, we're talking about the same type of problem. We have discharge flowing in a pipe. That, of course, is generating friction losses. And when our energy losses are only friction losses, so here our energy losses are only friction losses. Now for the friction loss equation, we can either use Darcy-Weisbach or we're saying we can use Hayes and Williams. Again, you will not get the same answer if you use both equations, so you should be aware of that. So, when we look at those three classes of equations, three classes of problems for the closed conduit flow, calculating energy losses, for example, this first equation is taking the Hayes and Williams equation, the first equation on today's handout, and rearranging it to solve for H sub F. Remember, in that equation, the friction slope is H sub F over L. So we take the Hayes and Williams equation, make this substitution, and then rearrange to solve for H sub F. The second class of equations for pipe problems is the discharge problem. And again, for the Hayes and Williams equation, we just multiply the velocity times the cross-sectional area and we get discharge. So again, for the discharge problem, you know everything on the right-hand side of the equation. The Hayes and Williams roughness coefficient is dependent on the material. The cross-sectional area is the cross-sectional area of the pipe, which you know in this class of problems. And again, in the discharge problem, what you typically have is a specification. Keep, for example, the pressure drop or the friction loss below a certain criteria. So that's how we did the problems when we were doing the Darcy-Weisbach form of this friction loss problem. And in this case, you would do the problem the exact same way, only here you're using the Hayes and Williams equation. And again, this is a direct solution because you know everything on the right-hand side of the equation. And then the last class of the problems, which we're working with, in which we have closed conduit piping systems, and the only energy loss is due to frictional resistance, is the pipe sizing problem. So here in the pipe sizing problem, all we did was take the Hayes and Williams equation in terms of discharge. So it's this equation, and we put in the cross-sectional area of a pipe, pi over 4d squared. The wetted perimeter is pi d. It's just the circumference of the pipe. And we rearranged and solved for the diameter. So again, everything on the right-hand side is known in this class of problems. And so again, when we use the Hayes and Williams equation, it's a simpler solution path than it was when we used Darcy-Weisbach. And that's again why the old timers like it. So, one big note. With the Darcy-Weisbach equation, we can either have it as we've always seen it, or when we identify that velocity is discharge over area, we can substitute for V squared, Q squared over A squared. And when we do that, we can then take everything except Q squared, factor it out. So the Darcy-Weisbach friction factor F times the distance between the 2 points of analysis, L, divided by 2G pipe diameter times cross-sectional area squared, times Q squared. That FL over 2G dA squared is just a coefficient. Let's call it the Darcy-Weisbach coefficient. And so what you see is friction losses are proportional to diameter squared. And if, in the last lecture when we were talking about the pipe sizing problem, friction losses are inversely proportional to d to the fifth power. So again, we're just lumping a lot of variables together to get this form of the equation. If we then look at the Hazen-Williams equation, when we rearrange that equation, which you had on a previous slide, to solve for the friction loss, again, instead of velocity, we're going to substitute discharge over area. Again, we can pull everything out of this Hazen-Williams equation except for the discharge and leave the discharge all by itself. And when we do that, what we get is, again, some factor, which we can just call the Hazen-Williams factor, KHW, times the discharge, and now you see the discharge is to the 1.85 power. So, you know, I've said it a few times today, and I'm going to stress this. Don't expect to get the same answer out of these two equations. If you're doing an analysis, you pick one equation and stay with it. Don't mix and match, ever. The interesting side note is, way back when, in the very, very first lab of this course, it was a lab that everybody did by themselves on logarithmic plotting, fitting a power function to data. And then subsequent labs, hopefully you were using that. But in this case, what you see, in general, not just friction losses, but in general, when we're studying pressure distribution systems, we say that the energy losses, HL, and again, this could be friction, and it could include also the minor losses that we're going to talk about today, are proportional or equal to, in this case, some factor times the discharge to some power. If it was just friction losses, that power would be 2 for the Darcy-Weisbach equation, and it would be 1.85 for Hazen-Williams. And the K values would subscribe to KDW up above, or KHW, which you see also above. For the practical application, though, is in the field, what we may have is a pipe underground. And we may not know how many valves are in it, if there's any valves. Also, that pipe could have been put in the 1800s. So we don't know if there's big holes and leaks in it. We don't know the status of the corrosion until we dig it up. But we don't want to dig it up. We just want to understand the friction loss characteristics of the pipe. So what we typically do in the field is where you have a fire hydrant. The fire hydrant basically has a valve down at the bottom of it. And that valve, when you turn the top stem of the hydrant, that when you spin that opens the valve. And so what you can do is put a pressure gauge when you open the valve and measure the pressure at one location. And then on another fire hydrant, you can measure the pressure here. And now your problem is you need to know the flow in the pipe. And so what we'll typically do is open up one of these hydrants to create a really large flow. And very often we'll do this at night when we know there's not a lot of flow in the pipes, that people aren't using a lot of water. So this hydrant flow is dominating. And so in this case, if we take 0.1 at the first hydrant to the left and 0.2 on the right, what we would say is that the total energy at 1 is equal to the total energy at 2 plus all of the energy losses. And because this is a horizontal pipe with a constant diameter, this is basically saying that P1 minus P2 over gamma is equal to the head losses, and those are equal to KQ to the n. So in the field, what we will do is measure the two pressures, and when we measure the two pressures for a specific flow, we have one coordinate of HL and Q. We'll run various flows, and then what we do is we fit equations, a power function, to compute K and N. And in many applications, what we find is that N ranges from 1.5 to greater than 10. And remember, I'm going to write that above because I know I wrote it above it. So N, 1.5 is less than N is less than 10. Exclamation point. So what is this saying? HL is K cubed to the N. As N gets larger and larger and larger, remember for Darcy-Weisbach it should be 2. For Hayes-Williams it should be 1.5. But I've had field settings where it's 7. What that means is any little bit of flow in that pipe is dramatically increasing frictional resistance. And that's what people sometimes don't understand. If you go out there and just put the pressure gauges on the hydrants, you may have 70 psi, plenty of pressure. But once you open the valve, or once you have water flowing in the pipe below, the pressure just drops precipitously. So for example, in your house, you have 70 psi coming in at the curb stop. And once you turn on the faucet, it just dribbles. And that's because between the faucet and the curb stop, you've lost all of the total energy through friction losses. And that's why the Torricelli equation, if you remember it, the Orbis equation, what's happened is you've dramatically increased C. And so that C is representing all the energy losses in the system. So that's how we practically fold either Darcy-Weisbach or Hayes-Williams when we're looking at systems and you actually don't know what's underground. All you're trying to do is develop a model that reflects what's happening underground. Spinach for the brain. So the next topic I want to talk about today is non-circular cross-sections. So for example, the ductwork for air in many buildings is rectangular cross-section. But you could have pipes of any different cross-section. And in fact, a long time ago, our wastewater and stormwater sewers were teardrop shaped. And why that was is because with really low flows, that would magnify the depth of flow and therefore increase the shear stress on the bed to move solids. And those were meant to flow only partially full when they were put in 200 years ago. But once we increased impervious surfaces and increased the wastewater flows to these systems, now they flow under pressure. So the EGL is way above the top of these systems, and so they're flowing under pressure. So this conduit is basically all flowing under pressure. So it's a non-circular cross-section. So for these cross-sections, fundamentally, we still use continuity. Continuity, discharge is equal to velocity times area. We are still going to use, for example, the Darcy-Weisbach friction. You could use Hayes-Williams, I just introduced it, but again, in this course we focus on the Darcy-Weisbach equation. So we still want to use this for friction losses. If we're using the Darcy-Weisbach equation for the friction factor, we need to know relative roughness and Reynolds number. And in all of these, they had a diameter, which was the diameter of a circular pipe. And now what you're trying to do is use the Darcy-Weisbach equation for a non-circular cross-section. So how we come up with hydraulic equivalency is to take the characteristics of a circular section and match them to the same characteristic of a non-circular cross-section. And basically, in this case, whether it's circular or non-circular, the diameter that we have reflects the importance of the flow field, for example, in discharge, as well as the importance or the unimportance, lack of importance of the boundary layer. And, for example, relative roughness, case of S over D. So, for a circular pipe, the geometric properties, or what we call the hydraulic elements, the area for a circular pipe, flowing full, of course, is pi over 4d squared. The wetted perimeter, again, is that part of the cross-section that is wetted by the fluid. And for a circular pipe, that's pi d, the circumference. And the hydraulic radius for a circular cross-section, hydraulic radius irrespective of the cross-section shape. Hydraulic radius is always defined as cross-sectional area divided by wetted perimeter. And for a circular pipe, remember that's the title of this slide. For a circular pipe, pi over 4d squared divided by pi d is d over 4. And that's what we're going to use, this relationship for an equivalent or non-circular pipe cross-section. We're going to just say that the equivalent diameter is 4 times the hydraulic radius of the non-circular cross-section. So basically, in the previous slide where I had Darcy-Weisbach friction factor, relative roughness, Reynolds number, wherever you see the diameter, we're going to replace it with 4 times the hydraulic radius. So instead of FL over D, V squared over 2G, we have FL over 4RH, V squared over 2J. Continuity is still the real cross-section. Average velocity times real cross-sectional area. But for friction loss, instead of the diameter, which the Moody diagram was built around, we're using 4 times the hydraulic radius. For relative roughness, instead of K sub S over D, we use K sub S over 4 times the hydraulic radius. And for the Reynolds number, it's velocity times 4 times the hydraulic radius over mu. So the types of problems are all the same. The friction loss problem, the discharge problem, or the pipe sizing problem, only now instead of the size of a circular pipe, what you're going to calculate is the hydraulic radius of whatever cross-sectional shape you want. So that's how we address non-circular cross-sections. And now I want to move into what we're going to talk about for the rest of this lecture. Today I'm setting up a lot of things, and Monday I will do a lot of examples. A lot means I'll probably have 3 or 4 examples, and that's it. And then we're going to move into open channel flow. So, minor losses are basically what's happening with minor losses. Anytime anytime you are converting velocity to pressure or pressure to velocity, you incur a loss over and above frictional resistance. Anytime you change the velocity vector. So one way to change the velocity vector is by converting velocity to pressure back and forth. That happens in an expansion, for example. So in an expansion, you're going from a really large velocity to a small velocity, and in a contraction, you're going from a small velocity to a large velocity. So that would be changing the magnitude. But also in a bend, what you're changing is the direction of the velocity vector. And whenever you change the direction of the velocity vector, again, what you're generating is an increase in internal turbulence, which there, as a result, generates additional energy losses over and above friction. So what happens is, when we're going through something like a valve, the EGL is coming in, we just have pipe friction, and in the valve, we're going to see a loss in the energy grade line. And that loss is a minor loss. And in this case, I'm just going to subscript it HV because we have a valve there. And yes, there is frictional resistance, which is happening in the valve, but you don't double count. You will see that when we come up and calculate the energy loss just due to a feature like this, it includes the frictional resistance as well as the inefficiency of converting from velocity to pressure, as well as the fact of the increased turbulence if you're changing the direction of the velocity vector. Okay, so you don't have to calculate a friction loss within a feature where we have minor losses. If you think about it, a gradual expansion at the end, at the limit, is an exit where you go from a pipe into a large reservoir. And a gradual contraction at the limit is a pipe entrance. And when we get to talk about the table, I'll put those out to you. So, just to give you a feel for how we use this, here's a piping system. And for this piping system, let's say we want to sketch the energy grade line. And for the energy grade line, I'm going to start at this bend so it doesn't get too busy. So, at the bend, we have a drop in the energy grade line because at a bend, we have a minor loss because we changed the direction of the velocity vector. We have energy losses over and above those due to friction. And then in the smaller diameter pipe, the 4-inch commercial steel pipe, we have energy losses just due to friction. And that's why you have a constant slope to the energy grade line. If we took that total drop and divided it by the length, we get the slope to the energy grade line. And then at the sudden enlargement, again, we get an energy loss just due to, in this case, the expansion. Now, I've drawn it as a slope, but realistically, we typically draw it as a vertical line right over the feature itself. And then once we go into the larger pipe, the 6-inch diameter pipe, what you see is the energy grade line has a much flatter slope. Remember, as we pointed out today as well as yesterday, the friction losses are inversely proportional to diameter of the power. So when you go to a larger diameter pipe, you have a much flatter energy grade line. And so if we looked at the components here, the drop in the bend is HB. And then between the bend and the enlargement or the expansion, we have friction losses, HF, and I subscripted that 4 because it's the friction loss in the 4-inch pipe. And then we have the energy loss, the minor loss of the expansion, the sudden enlargement, and then we would have friction losses in the 6-inch diameter pipe. And the synthesis of all of this, if we selected 0.1 at that upstream bend, flow is left to right, and 0.2 is at the downstream end of this system, we are equating the total energy, V1, to the total energy at V2. And they're obviously not at the same elevation. And so in this case, V1 plus V2, V1 is equal to V2 plus the sum of all energy losses we had between points 1 and 2. And those energy losses would include the loss in the bend, the upstream, the friction loss in the 4-inch pipe, the minor loss due to the expansion, and the friction loss in the 6-inch pipe. So what that would look like when we expand V1, we get V1 squared over 2G plus P1 over gamma plus Z1. When we expand V2, V2 squared over 2G plus P2 over gamma plus Z2. And then again, we have friction losses, HF in the 4-inch pipe plus HF in the 6-inch pipe. That's what the sum of the HF represent. And for minor losses, we have a bend and we have an expansion. So now we have to just see how we calculate the minor losses, because we know the friction losses are H sub F is equal to F L over D, B squared over 2J. So to find HF4 and HF6, this is that first class of problems. Calculate the friction loss knowing a bunch of other information. So you would need to calculate the relative roughness, the Reynolds number to get the friction factor, and then you know the pipe length between, of just the 4-inch pipe, between the bend and the sudden enlargement, and if you know the discharge, you know the velocity of the pipe. So minor losses are either, these are fittings, and these are appurtenances. So, again, anytime you change the magnitude or direction of the velocity vector, you get a minor loss. The minor losses are all calculated this way. And if you have your textbook, it should be on page 270 of your textbook. It'll be on the next page. So what we have is the velocity head. And the one issue that is going to, all of a sudden, you're going to face it on the exam. And you're going to have the deer in the headlights moment. Think of the expansion. Or if flow is going from left to right, it's an expansion. If flow is right to left, it's a contraction. And the problem you're going to face is, which velocity head do I use? So you should write this down. Always use the velocity associated with the smaller diameter on either side of the minor loss feature. And so, for example, look at a pipe entrance. Remember, when you hear the word entrance, what's happening is you're going from a large reservoir into a pipe. And obviously, in the reservoir, the velocity, we've always said, is basically static. It's zero. And if you unfortunately selected that, which is the larger diameter when you compare the reservoir to the finite diameter pipe size, you would have a velocity of zero if you use that as the reservoir. And it's the same thing for an exit, where you go from a pipe into a large reservoir. Always use the velocity associated with the smaller diameter, and you'll never go wrong. So Km is a dimensionless loss coefficient, and typically you can go, for example, in your fluids book on the next page of the slide presentation, I'll go over these, but if you are sizing a system, if you're designing a system, and you're going to select certain valves, let's say you're putting in gate valves, which typically are used to isolate lengths of pipe, they're either open or shut, and you want to know the loss coefficient, the manufacturers all have this information. If they cannot provide you with that information, why would you be buying their product? And so the manufacturers all have this information. It's not like it's a mystery and we're the only ones who have heard of this. This is readily available from the manufacturers. So on the next page of the PowerPoint is page 270. I think it's table 710 maybe from your textbook. Table 10.5 from your textbook. It's the minor loss coefficient. So in the heart of the table, all the numbers that you see in this table are Km, the loss coefficients. So again, for a pipe entrance, typically if it's square edged, we'll use a loss coefficient of 0.5. If you use rounded entrances, which are going to be much more expensive, you can drop that loss coefficient. You can see contractions depending on the angle, whether or not it's abrupt. So an abrupt, if it's an abrupt contraction, that's 180 degrees. And if it's a gradual contraction, you can see the minor loss is a little bit lower because you're gradually changing the velocity vector rather than doing it dramatically. But also, for a gradual contraction, you have this blunt wall, and that's creating a lot of excess turbulence in that location. So that's why the abrupt contraction would have a much higher energy loss coefficient than a gradual contraction. And the other thing, remember, at the limit, a entrance from a large reservoir to a pipe, at the limit, this is a contraction. And as we said, for entrance, you've got typically a loss coefficient of half a velocity. 0.5 is the loss coefficient. And then conversely, for the expansions, again, it depends on how severely you're changing the diameter. But when you're looking at an abrupt expansion in this case, and you're looking at going from a finite pipe size into a large reservoir. This would be the exit loss coefficient. And so typically when you go from a pipe into a reservoir, into a, say, a water storage tank, you lose one velocity head. The loss coefficient is 1. So you should be aware of those two values. And then again, there are many different types of bends. And this table is just giving you a few of them, as well as there are a number of different types of valves. But the important thing is when you have a problem in front of you in this course, you need to look up the loss coefficient for the feature, whether it's a bend, a valve, a connection, whatever, that's in that problem. And then once you have the value of Km, then the minor loss is Km v squared over 2J. So, in an example, what is the energy loss associated with a wide open globe valve in a 4-inch diameter water pipeline? The discharge is 300 gallons per minute, and the pipe on either side of the globe valve has K sub s equal to 8.5 times 10 to the minus 4 feet. And just to go back, for the globe valve, here's a wide open globe valve, go figure. We can see that Kg, I subscripted G because it's a globe valve. When you have a lot of different minor loss components, it's not a bad idea to use a subscript that describes that component so that when you're reviewing your work, or better yet, when someone's checking your work, they can associate the loss coefficients. So in this case, Kg is 10.0. So we have a discharge of 300 gallons per minute, and again, with all of our equations in VGS, we typically use pound, foot, seconds. So 300 gallons per minute is 0.668 cubic feet per second. The velocity is discharge over area, so we've got a 4-inch diameter pipe. We can calculate the area, and from that get the average velocity, 7.66 feet per second. We can calculate the velocity head, v squared over 2g. G is 32.2 foot per second squared. That gives us a velocity head of 0.91 feet. We just looked up the loss coefficient, the minor loss coefficient for the globe valve, that's 10. And so the minor loss associated with the globe valve is K globe valve v squared over 2g. And again, v and v squared over 2g are associated with the pipe outside of the minor loss feature. And again, if there's a different size pipe on either side of the feature, you always take the velocity associated with the smaller diameter pipe. In this case, we have a 4-inch pipe on both sides of the globe valve. So there's no decision. Not uncommonly, what people do for modeling purposes is identify an equivalent pipe length in which that pipe length generates the frictional resistance equivalent to that minor loss. So basically what they're saying is, I just calculated the minor loss of the globe valve, and that's equal to 9.1 feet. And you can see I also converted that to 3.95 psi. What we're going to do is say, if that was due to just friction, what would be the length of pipe that would cause that amount of friction loss? So basically, now that we have the 9.1 feet, what we're going to do is let the friction loss be equal to the loss of the globe valve, and just solve for the equivalent pipe length, which is known as LE, by using the Darcy-Weisbach equation. So we know the velocity, we know we have water, we know the pipe is a 4-inch diameter, we can calculate the Reynolds number, velocity times the diameter over kinematic viscosity. You were given in the problem above the diameter and the absolute roughness, so we can calculate the relative roughness, and we can then either go to the Moody diagram or use any of the equations that describe the Moody diagram and find out a friction factor. So again, in the Darcy-Weisbach equation that I put over to the right, what we have, we know the velocity, we know gravity, the diameter is 4 inches, and we just found F. And we know that h sub F is 9.1 feet. So all we're doing is calculating an equivalent pipe length. And when we do that, we get, it would require almost 131 feet of pipe to give you the same energy loss as represented by this one valve. So, now that we have non-circular sections, minor losses, friction losses, we still have the same 3 problem types. It's just that the energy equation is getting more complicated. That's all. It's the same classes. And in these classes of pipe, now what we're saying in all of these is we start off with an energy equation between 2 points. The head losses, or the energy losses, are maybe multiple sections of pipe with friction and multiple different minor losses. So for example, you can have a pipe and it's going from one reservoir to another reservoir. And you can see there's a bend here, and there's a bend here. There's an entrance. The pipe flows from left to right. You know which way water is flowing in this case because of the difference in the reservoir water elevation. Remember, the water surface of a reservoir is the energy grade line, and fluids move in the direction of decreasing EGL. So you have an entrance on the left reservoir and an exit over here. And let's say you have 2 valves here. And they can be the same valve. And so when we expand this energy equation, V1 is just the energy grade line, the water surface of that first reservoir. P over gamma is 0. If 0.1 is on the surface, these 1 squared over 2g is 0. That's equal to Z2, because again, if 0.2, you should always label your points, Tom. If 0.2 is on the surface of the second reservoir, its energy grade line V2 is just the elevation, plus, and let's just charge through it. We have K entrance, V squared over 2J, plus we have a length L1 of pipe between the reservoir and the first bend. Then you have another length, L2, another length, L3, L4, L5. If it's all the same diameter pipe, the friction loss is the sum of the friction loss in all of that pipe. So you don't have to break out FL1 over D V squared over 2G, FL2 over D V squared over 2G, because again, they just sum up. If they're not the same diameter, then obviously you have to break them out. Question?
Yeah, we have a request to go back 1 slide.
Is that it?
That was the request, yes.
Pardon me?
That was the request, yes. I think they just need to finish writing. Yep, all set.
Excellent. So after the entrance, and now we've accounted for all friction losses, then we have the second bend, and actually we have 2 bends, and if they're the same, 2K bend, V squared over 2G, plus we've got 2 valves, 2K valves. If they're the same valve, if they're different valves, you have to break them out separately because they would have different loss coefficients. Plus the exit. And so what that would say is that Z1 minus Z2 is equal to the sum of the energy losses, which is equal to, in this case, F L over D plus K entrance plus 2K bend plus 2K valve plus K exit all times V squared over 2K. So again, you would knock out everything on the right-hand side, but this fundamental equation would be used for any three of the classes of problems on this slide. That's your starting point. They all start with an energy balance. So I see that there is only 30 seconds left, so I'm going to leave you with a rhetorical question. What about mechanical energy, you say? So Monday we're going to talk about doing examples, and I'm going to throw pumps and or turbines into the mix, but it's the same thing we did a long time ago when we had zero energy losses. It's the exact same analysis. So have a great weekend, stay healthy, and we'll see you Monday. Expect to see a homework problem if I get my act together and work them out.